In this segment, we're going to talk about resonance structures, which are multiple different ways that we can show electrons being arranged within a particular molecule. When we talk about resonance structures, these are going to be one of the foundational aspects of organic chemistry because they're going to be one of the central themes that allows us to determine why some molecules are very reactive, why some molecules are very unreactive, and they're going to be very essential in helping us justify why some compounds are very stable, why others are very unstable, and we're going to see resonance coming up pretty much in every chapter of this semester and onward. Resonance is one of those fundamental concepts of organic chemistry that we really can't do without. It is going to help us explain a wide variety of different phenomena and observations that we will make as we go through. So we need to start laying the groundwork of understanding resonance structures and what they mean to us. So the idea of resonance structures is that when we draw a Lewis structure for an organic molecule, we plug in the different lone pair electrons and the pi bonds and things like that around the molecule, that there are typically going to be multiple different places where those lone pair electrons and pi bonds could possibly be in many cases. And so if there's multiple possible places where we could physically locate those pi electrons or lone pair electrons, we're going to talk in terms of the molecule having different resonance structures. And if there are different resonance structures possible, different places where the electrons could be located within the molecule, then what becomes the actual case, the actual scenario, is that the actual electron placement is an average or a hybrid of those different possibilities. And that hybrid or average is determined by the relative stabilities of the different resonance structures, where the more stable the electron arrangement, the more favorable that is, and therefore the more it's going to contribute toward the average. And when we think about that actual electron placement being a hybrid or an average of the possible places that electrons could be on the molecule, keep in mind that the individual electron arrangements that we can draw out on paper are not the actual case that exists in real life. Instead, the actual structure is an average of those possibilities. It's not like the molecule is rapidly switching from one electron configuration to another. Instead, it's a hybrid that has some characteristics of each of the different structures that we could draw. One analogy is that you could think of it as being like a mule. So a mule is a hybrid between a horse and a donkey. And it's not like the mule during its life oscillates between being a horse or looking like a horse and looking like a donkey. Instead, it looks like a mule. It looks like an average of those two different types of structures that it originated from. Much like with resonance structures, the actual electron arrangement of the molecule is reminiscent of an average of the different possible structures that we could draw, the different parent structures that we could draw of this molecule. So we're going to take a look at how we go about drawing these so-called resonance structures, the different electron arrangements that we can see within a particular molecule. And we're going to use these resonance structures as tools to understand a variety of different attributes of the structures and stabilities of molecules. So we're going to start by looking at and writing down the so-called rules of resonance. These are the criteria that we have to meet when we're thinking about writing different ways to show electrons surrounding atoms within Lewis structures or other types of structures of molecules that we can draw. So we're going to look at the rules of resonance, what we have to fulfill, the criteria that are the must-haves for drawing different resonance structures. So without these rules being met, the resonance structures cannot exist, period. After we go through these rules and get a firm grasp on those, in the next unit or so, we're going to look at the criteria that will determine whether a resonance structure is a major contributor toward the weighted average or hybrid structure, or whether it's a really minor contributor. But for first, we need to determine what are the ground rules for resonance. So first off, if we're thinking about drawing two different electron arrangements of a single molecule, which is what resonance is by definition, the first thing we have to keep in mind is that we can't create or destroy electrons along the way. Every single structure that we draw has to have the same number of electrons. If we've changed the number of electrons, the two molecules are no longer resonance structures of one another. We've done something wrong. So every structure that we draw has to have the same number of electrons in total. We're going to focus primarily on the valence electrons, so I'm going to just put all structures must have the same number of valence electrons, because it's those valence electrons that we're showing in our different molecular structures that we draw. So all structures must have the same number of valence electrons. All right, so all we can do during resonance is we can move those electrons from one place to another within the molecule to show the different possible electron arrangements. We can't create or destroy electrons along the way. Rule number 2 is that no structures can exceed the octet rule. That is for the atoms that follow the octet rule, such as most of the things we deal with: carbon, nitrogen, oxygen, halogens, etc. So we're going to add to our list here, no structures can have atoms, and we're going to specify that those are the typical atoms that we see in organic molecules. There are some oddball atoms that can exceed the octet rule, but we're looking here in organic chemistry at carbon, oxygen, nitrogen, halogens, where we define halogen as X. So no structures can have atoms that exceed the octet rule. So going over the octet is a never, never rule. We can never exceed the octet. So the operative word there is exceed. What I do want to make you aware of, and a common misconception here, is whether or not we can be under the octet rule. And you can go under the octet rule. Typically, that's going to correspond to resonance structures that are not as stable as some of the other possibilities, because the octet leads to a lot of stability. But we can be under the octet rule in some structures. So, okay, to be below the octet rule. You just can never be above the octet, or the resonance structure is a definite no-go. So step 3, or item 3 on this, rules of resonance. When we're drawing resonance structures, the only thing we are allowed to move within the molecule are the electrons. We can't relocate the atoms. So when you think about drawing resonance structures for different molecules, we're going to leave the placement of the atoms exactly the same and going from one resonance structure to another. So you can just pretty much redraw the same skeleton over and over and over again, and you're just going to be moving the electrons around within that skeleton. So structures must differ only in the electron arrangement, not in the location of the atoms. If you start moving atoms around, you're creating different constitutional isomers, not different resonance structures. So structures must differ only in their electron arrangement. The atoms themselves are locked into place. So another thing that we can use to follow up on this is, or another way to put it, is that when we're going from one resonance structure to another, you will only move the electrons in going from one resonance form to another. So only move electrons during the drawing of resonance forms. You're never going to be moving atoms during that process of drawing different resonance forms. And as a follow-up to that, keeping in mind that the atoms have to stay in one place, what that is going to mean to us is that the single bonds have to stay in one place as well. So when we're drawing resonance structures, the electrons that we're going to be moving are going to be the pi electrons and lone pair electrons, not the sigma bonds. The sigma bonds are the single bonds. So guideline number 4 here for our rules of resonance is the single bonds tend to generally be very, very stable. And we're going to see when we do chemical reactions later on in the semester that in most cases the single bonds are going to stay in place between carbon atoms and carbons and hydrogens and things. And it's generally going to be the pi bonds and the lone pair electrons that are doing the work in the chemical reaction. So similarly, when we're doing resonance, don't move the sigma bonds, where the sigma bonds are single bonds. Instead, what we're going to move are the pi electrons, and the lone pair electrons are going to be the ones that are going to be fair game for doing the work of resonance, for moving around and being able to be located in different locations within the molecule to create these different hybrid structures. So then the next thing to keep in mind when we're looking at resonance is that if we have a pair of electrons both of those electrons of the pair typically have to move together to form resonance structures. So you have to move both electrons from the pi bond or both electrons of the lone pair when we're drawing an additional resonance structure. So in general, we're going to see that both electrons from pairs move together. And when we say both electrons from pairs, we're referring to both electrons of a covalent bond or both electrons from a lone pair. So the only exception to that is going to be, we'll look in a few chapters at radical reactions, which involve unpaired electrons. And we'll see in those cases, we will have some situations where we move one electron at a time rather than pairs. But for now, for these rules of resonance, we're going to focus on moving both electrons of a pair together at the same time when we're doing a resonance structure drawing. So let's take a look at applying these rules of resonance, which I'll try to leave it here in the upper left-hand corner for us to refer back to drawing different resonance structures for a couple of different organic molecules here as our example problems. So we're going to start with the example problem of acetic acid. Acetic acid is what gives vinegar its highly distinct odor and flavor. And this acetic acid structure, we're going to start with a 2-carbon chain that includes a carbon-oxygen double bond. That carbon-oxygen double bond is referred to as a carbonyl group. And I'm going to go ahead actually and start off by drawing this as a condensed structural formula, like so. And then we're going to try to show all the different resonance structures. For this. And so in order to do that, what I'm going to do is redraw this structure with a little bit more detail about the bonds that are present in the molecule, because when we're going to show resonance structures, it's usually essential that we show some of the covalent bonds and certainly all of the lone pairs, since the lone pairs are one of the things that are able to move about in going from one structure to another. So what I've shown here is kind of a hybrid in the middle of the page here between a Lewis structure and a condensed structural formula, where what I'm really trying to emphasize in the way that I've drawn this is I'm trying to emphasize the lone pair electrons and the bonds that are going to be involved in resonance. So we'll start with this structure, and then we're going to try to show the different resonance forms for this. And when we show two structures that are related as resonance structures, we have a very special arrow that we use to show that. That arrow is this double-headed arrow right here, which is always going to be used to denote resonance. Don't confuse this with an equilibrium arrow or any other type of reaction arrow. This arrow, the single arrow with two heads on it, is always used exclusively to denote resonance. So it is definitely not the same as an arrow such as what I'm drawing up in the upper right-hand corner, which shows an equilibrium reaction. Resonance is by no means an equilibrium. Resonance is just multiple ways of showing the same exact molecules, not showing that the two are in equilibrium at all. It's showing that the actual structure is an average of the different structures that we've shown, not that we're switching rapidly between the two. So the arrow on the left shows an equilibrium reaction, arrow on the right shows resonance. Those two arrows are in no way, shape, or form interchangeable, so definitely don't make that rookie mistake. All right, so we're going to show the possible resonance structures here. And one thing to keep in mind as we're drawing resonance structures is that point number 4 of our list of rules of resonance is going to be really useful. And that is that when we think about what we can move for resonance, we're going to be honing in on the pi bonds and the lone pair electrons as being our mobile electrons. So I'm going to highlight here our lone pair electrons, our pi bonds within the molecule, because those bonds that I've outlined in yellow are the ones that we are going to be capable of moving. And when we start to think in practical terms about moving electrons, when we're moving these pi bonds and moving the lone pair electrons, one thing that will be kept in mind that is often a really useful technique to use to help us draw these structures properly is move your pi bonds and your lone pair electrons toward atoms that are electronegative, because atoms that are electronegative typically have a thirst for the electron density. So they're going to, generally, we're going to see that it works out that they can pull electron density toward themselves in this resonance structure drawing. And also, if you move the electrons toward atoms with a positive formal charge, that's typically going to be favorable as well. Remember, though, that you can never exceed the octet rule by doing this. So as we do this, we have to always keep in mind that you can't go over the octet rule in whatever structures you draw. You can be under the octet, but never over the octet. So let's take a look here at this concept of moving pi bonds and lone pairs toward electronegative atoms and toward atoms that have a positive formal charge. And one possibility here is that we could take the pi bond, shown in red, and it's adjacent to that electronegative oxygen atom. So what if we try to move those 2 electrons from the pi bond up onto the oxygen? I'm showing that with a red arrow here as our map, where the red arrow head shows where the electrons are finishing up at, and the starting point of the arrow here indicates where the electrons started off at. So we're showing that the pi electrons are moving from being a pi bond there connecting carbon and oxygen to those 2 electrons being situated at the end of this just on the oxygen atom. So we're going to draw this second resonance structure, and we're going to make sure, once we've drawn this, that it fulfills the criteria for the different rules of resonance. So I'm redrawing the structure. The only thing that I'm moving is that I've taken those 2 pi electrons from the carbon-oxygen double bond. I move those up onto the oxygen, so I'm going to show that in red. If you do your formal charge calculation, what you're going to find is that the oxygen has a -1 formal charge in this resonance structure. Carbon has a +1 formal charge in this resonance structure. So that's going to be a second resonance structure that we can draw for this particular molecule. But there's more. So what we can do, continuing onward and following again this theme of moving pi bonds and lone pairs toward electronegative atoms and toward atoms with a positive formal charge whenever possible. If we take a look at that structure on the right here, and we think about moving the electrons, the pi bonds or lone pairs toward atoms with positive formal charge, we have a couple of different options. One option is that we could take a lone pair from the oxygen, and we can move it down here to make a pi bond, as I've shown with the red arrow that I just drew on that structure. However, if we do that, what that's going to do is that's going to just revert us back to the starting structure that we drew on the left. So we want to make sure that we're drawing unique, different, new resonance structures rather than just repeating the same ones over and over again. So that's not really what we want to do here. Instead, what we want to do is follow this business about moving pi bonds and lone pairs toward atoms with a positive formal charge. So in this middle scenario, we have a carbon that has a positive formal charge. And so the oxygen lone pair electrons can come over to make a carbon-oxygen double bond. And that will enable us to draw a third resonance structure for this particular molecule. So we'll go ahead and draw in that third possible resonance structure. And I've shown the new covalent bond, that pi bond, in red. And as a result of this, we'll end up with an oxygen that has 3 covalent bonds and 1 lone pair. If we do the formal charge calculation on that, we're going to end up with a formal charge of +1 on the oxygen. One thing you will notice as a pro tip for resonance structures and getting these drawn correctly is that you should always notice that the net formal charge must be conserved. And the reason it has to be conserved is because we're not creating or destroying any electrons along the way. So therefore, the total net charge has to be the same. And that's going to be a net charge of 0 in all 3 of these different resonance structures that we can draw. Any additional resonance structure that we would draw here that would fit these rules of resonance, what we would find is that we would end up redrawing the same structure that we had already drawn once before. So the set of structures that I'm blocking off here in yellow is our comprehensive set of resonance structures for this particular molecule, for our acetic acid molecule that we've drawn here. And the relevance of this is that the actual structure, the actual electron arrangement of acetic acid is not represented accurately by any of these 3 structures. Instead, the accurate electron arrangement is an average or a hybrid of these 3 structures, where the actual electron arrangement has some features of each of these 3. So we can get ideas here from these different resonance structures about what portions of the molecule we would expect to be particularly strongly negatively polarized and what portions we would expect to be particularly strongly positively polarized by looking at the breakdown of where the charges end up in each of these individual structures and thinking about how strongly or weakly they contribute toward the actual resonance structure. So we'll leave it at that for now with those three resonance structures. What we will circle back to in a little while in the next part 2 portion of our resonance discussion is we'll look at how we can determine the relative contributions of these different three structures. In other words, which structure is going to be the major contributor toward the actual electron arrangement and which one is going to be a pretty trivial minor contributor. We'll get to that in the next segment after we have a chance to look at drawing different resonance structures and thinking about what possibilities exist there. So before we do that, let's look at another example of drawing resonance structures. So we'll do another example problem here, where we're going to show resonance structures now for this molecule. So we're going to start with a 6-membered ring, and I'm going to do a line angle formula here for our 6-membered ring. And generally when you're doing resonance structures, it's totally fine to use any type of structure that you are familiar with. So line angle formulas, Lewis structures, etc. The caveat is that regardless of what type of structure that you choose to use, you do typically need to show your lone pair electrons in order for us to understand how we're going from one resonance form to the next to the next. So we're going to start with the structure here that I've shown on the lower left-hand side, our 6-membered ring. And we're going to draw the different possible resonance structures for that, keeping in mind these different criteria that we've listed above, which I'll try to go ahead and keep showing here, at least in some small fashion, for our reference. And by the way, resonance structure drawing is one of those critical skills that you're going to be in sad shape without. As a result of that necessity of drawing resonance structures, there is an entire page of the Chapter 1 worksheet that deals just with drawing different resonance structures for molecules. So you definitely want to make sure that you get really on board with drawing resonance structures, because it's going to be something that doesn't go away as the semester goes on. It's just going to haunt you over and over again. So better off to tackle it now rather than waiting until later and suffering as a result. So we've got our structure, our starting structure here on the far left. I'm going to go ahead and fill in my lone pair electrons. Have to be 2 sets of lone pair electrons on the oxygen in order for that oxygen to have a negative formal charge of 0. And now what we're going to go ahead and do is draw our different resonance possibilities. So we're keeping in mind these 5 different criteria or rules of resonance that we've listed above. And we're also keeping in mind kind of these pro tips that I've put stars on right up here about moving the pi bonds and lone pairs toward electronegative atoms and atoms with positive formal charges, and the net formal charge has to be conserved if we're doing this correctly. So let's go ahead and do that. And what we're going to do is we're going to take the pi bond here, and thinking about electronegative atoms, because there aren't any atoms with positive formal charge, the electronegative atom is the oxygen. So what if we take those pi bond and move it up here? That's going to create for us a second possible resonance structure. So we will go ahead and draw the structure for that in just a moment. The other thing that might be on your mind as I think about possible places where you might go a little awry in this is you might think, okay, what if I move this pi bond from the ring up here onto the oxygen? That seems like something to do because we can move pi bonds and we're moving toward electronegative atoms. Okay, the reason that you don't do that is because when you're doing resonance, you have to move to the adjacent atom or the adjacent bond only. And here we would be taking, based on the arrow that we show, we'd be taking a pi bond from within the ring and moving it about 3 bonds or 3 atoms over. We can't do that. We have to move it over to the adjacent atom or the adjacent bond. And so that's why we're focused on moving from the pi bond right here up onto the adjacent oxygen. Otherwise, it's going to be a no-go. So let's go ahead and draw the resonance structure that would result from that process of moving our electrons up onto the electronegative atom or oxygen atom. So we'll leave the 2 pi bonds within the ring in place for now. I'm going to go ahead and show all sets of my lone pair electrons on the oxygen in red here for emphasis. We had 2 sets to start with. We brought in a third, so we're going to plug that in, and then I'm going to plug my negative formal charge in right there. It doesn't really matter if you put it in the upper left corner or upper right corner, just as long as it's there somewhere. I put it where it fit best, to be honest. All right, so with that then, we need to fill in our other formal charge here because our net formal charge to start with was 0. So we better make sure that our formal charge in our second structure is 0 as well. That means we need a positive formal charge on that carbon. We could calculate the formal charge there. to get that that has to have a positive formal charge of +1. So we'll go on to the next resonance structure. And looking back at our pro tips there, move the pi bonds and the lone pairs toward electronegative atoms, towards atoms with positive formal charges. Now we have an atom with a positive formal charge, and we can move our electron density toward that. So we can take the electrons from either of those two pi bonds, because both are adjacent to the positive formal charged atom. We can move those over to create a pi bond. So we can take the pi electrons from here and move those over. You'll notice that the arrow I'm showing shows that we start off at the pi bond electrons and we finish with those pi bond electrons moving over one spot to make a pi bond where the arrowhead lands at. So that's what we're going to draw the structure of here, is using the electron pushing arrow map. We're going to show that we've moved the pi bond over to here, and we've redrawn the atoms in exactly the same places as they were to start with. By definition, that's always going to be the case with resonance structures. And we haven't done anything to that oxygen up top, so I'm leaving it as is. But if we move that pi bond over, then what's going to happen is that our positive formal charge is going to have to end up landing right here. So we go ahead and do that. At this point, it's really handy to think about what number of carbons and hydrogens you have at each position to make sure that we're not stupidly going over the octet rule or naively going over the octet rule anywhere here along the way. So when we think about the carbons and hydrogens that we have, we can fill those in here if we want. We have a CH right here at the bottom, 6 o'clock position. We have a CH2, CH, and we do have to be careful down here where we have this CH2. A common mistake is that people will try to move electrons over to make a double bond somewhere around there, and they'll end up causing that carbon to go over the octet rule as a consequence of that. We definitely don't want to do that, because going over the octet is one of those game over mistakes. We definitely don't want game over at this early stage. So, all right, keeping in mind the different possibilities that we have here, we need to continue onward to figure out what else we could do, whether there's any additional resonance structures that we could create for this molecule, any additional places where we could move the electrons around to create additional resonance forms. And one additional resonance form that we can create for this molecule is that we could take the pi electrons from here, we can move those to right here, while we move these electrons back to here. So that's going to be another possibility. And so that possibility, we can go ahead and draw out the resonance structure that would result from that set of electron pushing arrows. So we're going to have a double bond right here, double bond right here, and the positive formal charge is going to end up landing right here, because that would be a CH group with 2 additional covalent bonds. So it's a carbon with just 3 bonds, so therefore it's going to have a positive formal charge. The other alternative way that you could have gone about showing this would be that rather than showing these 2 structures right here, you could have broken this into 3, where it would have been acceptable. So I'm just redrawing the structure up top there for starters. So you could have taken that structure and you could have first moved the pi bond back over here to create a resonance structure like so. And the positive formal charge right there. And then you could have shown the pi electrons from the left coming over to make that double bond come into place. So a carbon-carbon double bond there and there. And then that would have allowed us as well to put the positive formal charge right there. So you'll notice that these 2 different routes that I'm boxing off in yellow end up accomplishing the same thing. They end up accomplishing the conversion of our starting structure on the left to ultimately the structure on the far right. The one on the bottom shows as a intermediate to getting from the left to the right side, that intermediate in the middle, which is fine. but it is possible to go directly from one to the other, showing these electron pushing arrows. So in other words, it is fine to show a couple of different electron pushing arrows occurring simultaneously. Typically, when drawing resonance structures, a rule of thumb is that you never show more than 2 electron pushing arrows taking place simultaneously. So the way we've shown up top is fine and is in some ways the preferred route because that avoids duplicating any structures. When we do the route on bottom, we end up duplicating that structure in the middle that I put 2 yellow stars on because that structure we also saw appearing already in our list of resonance structures over here. So much like when you were drawing constitutional isomers for molecules, you wanted to avoid drawing the same structures twice. The same is true here, that if you're trying to draw a complete set of resonance structures, the complete set, you want to make sure there isn't any duplication between different structures. So the full set of resonance structures is going to be exactly what I've highlighted here in gray as your complete set of resonance forms, because those are 4 different unique structures. And the reason they are unique structures is that we are moving the formal charge from one atom to another to another. So you might be looking at the last 2 structures on the far right-hand side, boxed off in gray there, and saying those 2 look awfully similar because I could rotate around the one on the right to make it look exactly like the one on the left. But when we're talking about resonance, we are assuming that all the atoms are staying locked in place exactly as they're written on the page, and that those 2 atoms that the positive charge are on are 2 separate atoms within the molecule, and therefore what these structures are saying is that that positive charge is shared over 2 different carbon atoms. So even though the 2 molecules are symmetrical for purposes of resonance, we consider them to be different entities because it's showing us that the positive charge can be on 2 separate carbon atoms there. So that is why we'll show them as such. So with that, we'll conclude this general discussion of going about drawing resonance structures, and we'll continue on in the next segment with talking about how we determine what resonance structures are going to be the major contributors, because not all resonance structures are going to be equal contributors. Not all are created equal in terms of how they do or don't contribute toward the actual hybrid structure. So we'll look at that concept next time around.